All right, welcome back. Today we are going to discuss about the piezoelectric sensors and the Hall effect sensors. So till now we have seen the principle behind the capacitive and the resistive sensors, and we have seen some of their examples, the real world examples, the applications in the industries or maybe in the day-to-day life. And also we have gone through magnetic sensors, which are based on the principles of electromagnetics, which include inductive sensors, reluctance based sensors, and the eddy current based sensors. Now with these all study of sensors in this module, actually we are trying to understand the one of the important things in the industry 4.0, which is about actually the automation, or you can say mechatronics, that plays a major role, where we would have these sensors being used rather than the traditional or the classical, simple electromechanical sensors that were used in the classical times. So we need to understand there were issues actually, with the mechanical sensors. There's a lot of friction. There are other issues, inertia, and other issues that are used, so that are there. But with the obviously development of the semiconductor technology, we're able to develop these sensors, which are actually kind of mechanical again in nature, but they are more sophisticated. Electronics goes into their design, which makes them actually more electronic based. But because they have an application in the industries, and they follow some basic physics, the basic physical principles, or the principles of physics. So as mechanical engineers of the contemporary times, we need to understand their the principle behind these sensors and their function and their application, and also their limitations. All right, so let's talk about the piezoelectric effect. Now, this is something very classical to the students also, because piezoelectric is something that we have already studied in our times, that there are some materials called as piezoelectric materials actually, which produce an output voltage, or which produce a voltage when some forces are applied to them, or when they are put under stress. Now, such distortions because of the forces or the stresses actually causes something called as orientation of the electric charges within that material, which obviously results into the development of the positive and negative charges, and this kind of induces surface charges on the material of opposite polarity between the two sides. Now, by implanting electrodes on the surface of the material, these charges can be measured as an output voltage between the two ends of the material. So you can see on the right that there is an animation of a piezoelectric disc, a material which is being compressed or allowed to move, expand. Accordingly, there is change in the potential between the two ends of the material. So these are some naturally, and there are some synthetic piezoelectric materials. Sorry. Now, the induced voltage in a rectangular block can be given by capital K F D by A, where capital K is the piezoelectric constant, F is the applied force in grams, and capital A is the area of the material in millimeter square, D is the thickness of the material. So it is dependent on the geometry, which includes the thickness and the area, but it is also dependent on the force that we apply. But more than that, it's also dependent on the type of material for which piezoelectric constant would vary. So obviously it will depend on the type of material that is compressed, on the type of material, on the criteria whether we are actually compressing or stretching the material. Accordingly, we will have the induced voltage on the surfaces of the piezoelectric material. Now, some of the naturally occurring quartz, Russell salts, topaz, etc. And we have synthetic piezoelectric materials that we can actually make them in the labs. So lithium sulfate, ferroelectric ceramics such as barium titanate. So we can make, or we can reorient them, or we can actually make such materials which will have a certain definite properties that we would like to desire. So one basic example of a piezoelectric application, where you would have seen a lighting, a lighter, a small lighter that we use day-to-day life for burning the gas stoves and other things. So we have a piezoelectric element at this point, and then we press it. The moment we press it, so there is, because of the spring that is attached, so we actually have a force that is applied on the material, this element, and it causes a charge to be developed, and because of the gas supply, we have a flame produced at this. So this is one of the standard applications that we use in our day-to-day life, in our domestic lighter also that we use in our homes, that also has a piezoelectric a material, or you can see piezoelectric element installed in those lighters. So obviously this constant varies between different materials. So for example, this is very small for quartz, or for barium titanate, which is a synthetic piezoelectric material, it is quite high, which is equal to almost 140. So we can always make such materials. We can synthesize them in the labs, which could have very good amount of piezoelectric constant K. Now this could be obviously put under stress or under force in different ways. We can have thickness change. We can have thickness change. This is thickness shear. This is phase shear, and this is transverse change, where we try to actually compress or elongate in this direction. So obviously we can put these materials also, and we can do two things. One is we compress them and get a voltage, or in piezoelectric effect we have a reverse. They are reversible also, that we apply voltage and it causes deformations of the piezoelectric material. So to have a very high frequency kind of deformations, you can say compression and expansion, to generate something called as ultrasonic waves, also we use these materials for. So for such things we use something called oscillatory circuits like this, where we have some exciter in terms of some AC voltage, and we have some oscillating circuit, and then we have these polarities being connected to the piezoelectric material, and we can make it actually we can apply some voltage to the ends, which is kind of a changing voltage and having a very high frequency, which can generate actually a lot of vibrations in this material, which can cause actually something like development of sound waves and other things. So piezoelectric material can be used in both ways. We apply force and we get the voltage, and or we apply the voltage, we get the displacement, or you can say instead of force we have display, we displace this or deform this, and in the other case we apply voltage and we get the deformation. The applications are considerable. We have ultrasonic receivers, which are also called as displacement transducers. So they are devices for measuring acceleration, force, and pressure. So they can be used as ultrasonic receivers, actually the piezoelectric materials, because they can take the vibrations in the form of ultrasonic wave, and that can be converted to the voltage at the ends of the piezoelectric material. Similarly, we have it can be used as transmitters also, where they can act as kind of an actuator, where we apply a sinusoidal voltage of some frequency in the ultrasound range, typically more than 20 kilohertz, and which causes obviously sinusoidal variation in the thickness of the material, and it results in a sound wave being emitted at some chosen frequency. So both ultrasonic receivers and ultrasonic transmitters use actually piezoelectric materials in their basic as a basic component. Similarly, we can develop piezoelectric force sensors. We can have piezoelectric tactile sensors, piezoelectric accelerometers. It's also used as piezoelectric pressure sensors, and also in the microphones they act as sensors. Now let's look at the piezoelectric pressure sensors. So this is a cross-sectional view of the piezoelectric pressure sensor, where we have a diaphragm, and then we have something called as anvil plate, we have an insulating bush, and then we have a piezoelectric element placed here. So this is the part of the piezoelectric material that is placed here, cross-sectional view of that. So this black that I have highlighted is actually the piezoelectric material at this point. So as this end is actually connected to the measuring, you can say we can measure some fluid or gas pressure. So that is connected, the housing is connected to the this sensor, and accordingly the changes in the diaphragm or the deformation of the diaphragm actually will cause pushing, or can say forces on the piezoelectric material, which actually would lead to the development of charge, or you can say the voltage, and then that is taken by the the signal, or you can say circuitry that is attached, or you can say placed here, and then that is taken as the output to the our controller. So similar to this one, so we have applied pressure, then we have the piezoelectric element. These are the electrodes which take the voltage developed because of the applied pressure, and then that is fed to the controller. Now we can have a similar line diagram of this, where there is a pressure port which allows pressure to actually go through this one, and then there is a diaphragm, or you can say force summing member, and accordingly there is a crystal, a piezoelectric crystal, there is a voltage developed on the crystal because of the force. So we can use this as the pressure sensor also. Now they can be also used as accelerometers. So we have again a similar casing where we have a mass and the crystal that is placed here. Then we have, we can measure the vibrations, because the if it's put on a vibrating kind of an object, so that vibrations will cause deformation of the piezo crystal, and accordingly we'll have the output as the the as per the vibration we'll have output as the voltage over time. So this corresponds to the excited vibration on the object that is to be measured. So this is, let's say, displacement and this is time, so we'll have a voltage developed proportion to the displacement that is given to this. So we can measure the acceleration also. So they are also popular, called as piezoelectric accelerometers that are used. And so they operate from frequency as low as 2 hertz up to even 5 kilohertz, and they possess something called as good off axis noise rejection, high linearity, and a wide operating temperature. So these instruments have these features. You can also have a miniature type of piezoelectric accelerometer where we have a silicon structure, or you can say a silicon wafer is put, and then since silicon does not possess these piezoelectric properties, we rather put a thin film of lead titanate that can be deposited on this micro machined silicon cantilever that is used to fabricate an integral miniature sensor. So we have the MEMS technology. So these are the MEMS kind of, you can say, accelerometers that we use in our day-to-day life, in our mobile phones, in our cell phones that we use. We have something called as accelerometers inside the cell phone, and they look something like this, very miniature. They are all MEMS based micro electromechanical systems where the silicon wafer is actually at the core. And because silicon obviously will not have piezoelectric properties, but we can put up something called as lead titanate or any other such material that can be deposited on the micro machined silicon cantilever, which is actually used as the basis for designing an integral miniature sensor or an accelerometer. These are practically some view, can say, images of the piezoelectric sensors or accelerometers that are used in the industries. So obviously, for good frequency characteristics, a piezoelectric signal needs to be amplified by a charge to voltage or current to voltage converter, because generally what happens is we may have a small output in the form of a small voltage that is developed, which needs to be amplified, which needs to be filtered. Or we have in piezoelectrics, we generally talk about charge amplifiers or charge to voltage converters. So all such things may be required, and sometimes this may even be actually put up as a built-in in the same housing as the piezoelectric crystal. We also have piezoelectric force sensors. They look similar to this in the industries, and the principle is almost similar. So you have a force that is being applied on the impact cap. You have a preloaded strut or the stud, and then you have housing, you have an amplifier, you have a quartz element, that is the piezoelectric element here, or the crystal is here, and then there is something called a charge collection plate mounting hole. So the moment you press as an application of a force, so this compresses the piezoelectric material, and accordingly charge is developed, and that is amplified and then fed to the controller. Similarly, we have something called as tactile sensing that we use in haptics, or it's very popular. We used in our mobile phones. We use these touch pads and all those things. So they are also based on this piezoelectric principle. Though they have other principles like capacitive sensing and other principles can also be used. But here it's an example of a a piezoelectric based tactile sensor where you apply a force and then you have the piezoelectric film. This is a film created out of the piezoelectric material that is put up here, and then you have an oscillator actually, or you can say a force is applied and accordingly charge is developed, and then that's amplified and then taken as output. Also, this is used in the microphone sensor where you actually want to measure the the amount of, say, voice, or you can say noise. So we have a diaphragm that is actually connected to the piezo crystal. So as the sound waves hit this diaphragm, so it deforms or displaces this diaphragm, and accordingly it actually leads to the deformation of the piezo crystal. and accordingly we have a charge developed that can be measured, which can be corresponded to the the sound that is actually fed to the microphone. So it can be used as microphone sensor also. The key advantages of piezoelectrics is that they are unaffected by actually electromagnetic fields, external electromagnetic fields, because they're more dependent on the deformation and the production of charge. So there's nothing really magnetic in this actually in these sensors. So electromagnetic effects or the fields that are present in some places may not really have any problem to these types of sensors. It is obviously available in the desired shape, so you can have a square piezoelectric material, you can have a rectangle, you can have a triangle. So many desired shapes that we want to have, could be circular also. So that is available. That is good thing for piezoelectric actually sensors. So it's rugged in construction, smaller in size. This is how these sensors look like, which we are these pressure sensors or accelerometers are. This is how they look like in the real sense. They have a good frequency response, and how the output can be measured by the electronic circuit. But some of the limitations with them is that this output may not always be high. It may be very small in terms of the amplitude, may be very low. So you would need actually electronic circuitry or external circuitry in the form of amplifiers and these filters that has to be connected to this type of sensor. That could be called as the limitation. And also it is used for only dynamic measurements only, so we cannot use generally these for static measurements. So for static measurements, this may not really prove to have a very good result or an outcome. And it has high temperature sensitivity, so as the temperature increases or decreases, or in other harsh conditions, this may have different kind of impact on the performance on the instrument. So that is very important to be considered. And some crystals are water soluble. They get dissolved in high humid environments, and they are also prone to cracks due to overstress, because we're using them as sensors, and if there's an overstress, these crystals actually may crack. So that is about piezoelectric or piezoelectric sensors that we use as the principle, and then what are the advantages and the limitation. Now coming to the Hall effect sensors. So this was developed by Edwin Hall in 1879. This was observed though earlier, but this was formally developed or conceived in 1879 by Edwin Hall in a university in US. And it basically the principle is that it consists of a conductor, that is this brown colored square shaped. Let's say in this case we have, it doesn't really matter what shape you have, but let's say it's a conductor. It conducts electricity obviously. So now this is aligned orthogonally to the magnetic field. So there is a magnet, it could be permanent magnet. In this case, so it's a north and south pole. So it obviously will have the lines of force, or you can see magnetic flux that the magnet generally has. So because of the let's assume this conductor is actually connected to an DC supply, whereby there is current flowing through this conductor. Okay, now as this magnet is moved closer to this the conductor, or you can say current carrying conductor, as the magnet is made go closer to the conductor, what happens because of the Lorentz force, actually the electrons are displaced to one side. Okay, so electrons are actually kind of, you can say these are electrons, and they are all shifted to one side of the conductor rather than being uniformly distributed throughout. So what happens is there is a lot of electrons that go only on one side, and obviously the other side remains positive in a form of a charge. So there is a potential difference that is created between these two ends, which was actually not there before, or even if we put the magnet back, so it really would not exist. But because of the magnetic impact, or you can say because of the Lorentz force that acts on a moving electron in a magnetic field, so these electrons are shifted on one side and the holes are on the other side. So it develops a potential between the two, which is actually the Hall voltage, or you can say transverse voltage in a transverse direction. So this is the actually Hall effect. So the presence of magnetic field actually would deflect the electrons, and then the electrons move to the one end of the conducting material. A transverse voltage difference, or you can say the Hall voltage, is actually developed in a direction perpendicular to the gross current flow. So this is the gross current flow. The current that is flowing actually like this is flowing like this. Perpendicular to this, actually a current will start flowing, or a voltage will start developing. And if we tap these by electrodes, so obviously it will have a definite voltage. So obviously, and the current will also flow through this. So this will be because of this magnetic field. So this will directly depend on the strength of the magnetic field. Okay, so if the magnetic field is not there, so this type of voltage will not be developed. Now this type of effect was actually used initially in the detection of these magnets, or you can say magnetic objects, or you can say magnetic materials. This was the first application of this, but considerably, as the time progressed, as the technology progressed, so we have several applications actually of these Hall effect sensors that are used. The potential that is developed, obviously, as the Hall voltage would actually depend on the magnetic field, and hence it would actually tell us the strength of the magnetic field. So as we move magnet towards this, so the magnetic field strength is higher, so we will have a higher Hall voltage that will be developed. So this is again a line diagram where it shows the magnetic field direction, the forces that are acting on the electron as it is in through a magnetic field, that is because of a, let's say, permanent magnet on it. So this was the original current flow through this conductor, and because of this magnetic field there is a current in the perpendicular direction that flows through this, and which is called as the Hall voltage, or the transverse voltage that is developed because of the Hall effect. So this is the amount of force that will actually act on the electron, which is proportional to the charge, velocity of the electron, and also the magnetic field. So obviously, due to the magnetic field, this deflecting force shifts the moving electrons towards one side of the strip, which becomes more negative than the other side, which develops a voltage. So this is actually the Hall voltage, or you can say Hall potential difference, or you can say a transverse potential difference VH that is developed. And the sign and amplitude would depend actually both on the magnetic field and the electric current that is applied on the conductor. So at a fixed temperature, it is given by the transverse voltage, or the Hall voltage is given by HIB sine alpha, where alpha is the angle between the magnetic field vector and the Hall plate. All right. So if you can see from this diagram, so this is the Hall plate, and this is the magnetic field direction. So if it's not perpendicular, it will have some inclination with it, so that alpha will come here. All right. So as it goes to 90 degrees, sine alpha goes to 1. So we have HIB maximum. And if it's parallel to the direction of the current, so then we will have alpha is equal to 0, sine 0 is 0. So we'll have no Hall voltage developed in this type of. So there is a condition that it has to be perpendicular, or it has to be inclined to some extent with the direction of the current. And B here refers to the magnetic field strength. I is the current flowing across the conductor, and H actually is the coefficient of overall sensitivity, which actually depends on the plate material, or the geometry, and the temperature that we are working in. So accordingly, this H will also change. So these are the typical terminals of a Hall effect sensor. We have two ends of the Hall effect connected to a DC voltage supply, and then two ends are terminals that are taken as outputs, where we take this Hall voltage as an output. Now they are fabricated, they could be fabricated as at a macro level also, but generally we do them nowadays at a micro level. We fabricate them using silicon, because silicon is a conductor for us, or can it's a semiconductor also. So now two types are there, basic sensors and the integrated sensors. Now the basic sensors could be simple sensors that are developed out of, let's say, any conductor, and then we have other circuitry. But integrated sensors are generally, or you can say, IC, in which we try to actually interface this same circuit, that is the amplification, the filtering, and other things that are all incorporated actually in the same silicon wafer. So we develop these MEM devices, or you can say we develop all these integrated circuits like our amplifiers, or our operational amplifiers, or our MOSFETs and other things. We can also develop them at the on this at the silicon level, where we have at the MEMS level. So all this in the basic conductor and the other circuitry can be developed on the same silicon wafer, and we can etch it out at the MEMS level, and then we can have something like this as the Hall effect sensors. All right. Now this integration is important because the Hall effect voltage is generally quite small. This is how the circuit diagram looks like. So obviously you have this is the Hall effect sensor. These are two ends. Here the input voltage from the voltage regulator, and this is the output terminals, this one and this one. This is fed to an amplifier and Schmitt trigger, and then it's fed to the transistor for an output. Right. The applications are considerable for Hall effect sensors. You can maybe Google it also to find out how considerable are the application of Hall effect sensors. So you can measure magnetic fields. It can be used as proximity sensors and speed sensors. You can have rotary encoders also developed out of Hall sensors. So this is similar in an example of a rotary encoder where we try to mount this small magnets on the encoder, or sorry, on the shaft of the motor, connected with a disc. So as the magnet actually reaches near to the sensor, Hall effect sensor, so it actually generates a signal, which is the Hall voltage. So we get some, in the form of, we may get some output in the form of, this, and this. Where actually this refers to the point where the sensor goes to the on state. So we can actually count these, and also we can determine the position and also the speed of the rotating object, in this case the motor, let's say. Similarly, it's used in IC engine assembly lines for determining the position of the camshaft. These are embedded there. They can be used as contactless limit switches. They can, because we don't want to touch, can rather use them as limit switches. The moment it reaches near to the Hall effect sensor, we can actually generate a signal that okay, it has reached near to this, so we can limit our systems. And it can be used as automatic fuel level indicator. Hall effect switches, keyboard switches are also popular. It can be used in current sensing. It can be used in variable speed drives, motor control protection, and also as pressure gauges. Now, an example of a position and speed sensing that we just saw in the previous one. So we have a motor that is, whose speed and position needs to be measured. So we can connect even rather than one, we can have several Hall effect sensors to have a better precision. So rather than just having one sensor, we can have maybe a couple of sensors together. So as to give us more number of, let's say output. So we can have an output like this out of one sensor. Another sensor may give us an output of like this. And there could be a third sensor that may give us an output. So together we can actually improve the resolution also. So we can have such things. This is how a commercial Hall effect sensor also would look like. This is used in position again in the rotary cases where we have rotary motions. These are again similar, some commercial views of Hall effect sensors. It's also used as a liquid level detector. It's an example to show. So there is liquid in this tumbler, you can see in this tank, and then we want to create this as a detection level so that we can avoid overflow. So we have installed a rod here where a Hall effect sensor is provided this, and then we have a float that is actually moving along this rod. So as the liquid level raises, so this float will also raise, and there is a magnet provided on the float. So as it goes near to this detection level, the Hall effect sensor would actually detect this voltage as Hall effect voltage, and then we can send this signal to the controller so that the input to the tank is stopped, so that the overflow is avoided. The greatest advantage about Hall effect sensor is they are non-contact. So they don't contact the way we have said contact is limit switches. So they don't contact. They just come near to the magnetic material, or the magnetic material comes near to the Hall effect sensor. That's it. So you don't have to contact. So which means there is no wear and tear on this type of sensor. But the main sorry, that means we have no wear and friction. So hence unlimited number of operating cycles. So it has a high repeatable operation. So this is how even a simple Hall effect, linear Hall effect sensor actually looks like. So this we can use in our experiments or in our labs. We generally use them very easily. The main limitation is that this can be highly influenced by the presence of ferromagnetic components. So if we have a magnetic field and we want to measure some position or some other effects like that, but if we have some other ferromagnetic or magnetic components in the vicinity, so that they will disturb the Hall effect, this sensor output, because this is actually dependent on the magnetic kind of influence on the moving electrons. So as the magnetic field is made near to the electron, but if there's an external magnetic field that disturbs this magnetic field or interferes with this magnetic field, then obviously we will not have the correct output. So that's the biggest limitation with the Hall effect sensors. So again, it's not able to measure this Hall effect actually beyond a particular distance. So you have to be actually very near to the Hall effect sensor. If you're away from the Hall effect sensor, you may not really get an output as in Hall voltage. So this again another kind of limitation that you have to be actually near to the this Hall effect sensor, or the magnetic field would have to be strong enough to generate a magnetic field to make this possible. Also, temperature affects the electric resistance of the element and the mobility of majority carriers, and which is also related to the sensitivity of the Hall effect sensors. Thank you.